All right, so welcome to your last little bit of a lecture for the semester. So we're left off talking about different mechanisms that can break a Hardy-Weinberg equilibrium situation and cause evolution to happen, to cause not just changes in genotypic frequency, but also allele frequency as well. So we left off talking about migration as one of those mechanisms that can cause evolution to happen. And we're looking at an example where you have migration of 100 trout from a neighboring lake to a lake that we'd already been studying, and we know the p-value for each of those lakes. And from there, we could also calculate the Q as well if we wanted to. But the question you guys answered just before the end of class was, what is the p-value of the lake after the migration event? And a lot of you got this correct, which is great. For those of you who got it correct based on a good educated guess, let's go through the calculations you would actually do. I really wanted you guys to try to figure out the calculation on your own first, just because you understand the logic better than if I just gave you a formula and told you to plug in numbers. All right, so first thing you have to calculate is a value we'll call M, and that's the number of new trout introduced divided by the total number of trout in the lake after introduction. So essentially, this is the proportion. You're basically taking measuring what percentage of the final population is made up of the newly introduced trout, right? So in this case, for example, we have 100 new trout, and the total number of trout after migration is 1,000. All right, so that gives us 0.1, which basically says that 10% of the final population is made up of new trout. Okay, that's a helpful number to calculate in advance. So now let's define the remaining variables and symbols we're going to use in our formula and in our calculation. I'll show you the formula in a little bit, but first let's figure out what these variables and symbols are going to be. So PL is going to be the allele frequency of big A in our lake population, which is 0.6. So in the original lake population, we've seen in the question that the p-value is 0.6 before migration happened. Pn is the allele frequency of the trout population that these trout migrated from in order to get to the lake we're focusing on, which was 0.2, right? So the neighboring lake has a p of 0.2, and those are where the new trout are coming from, so Pn is 0.2. And so to calculate the p of the lake that's new after migration happened, right, this is our formula. Right? So 1 minus the m that we calculated times p of the lake, and then m times p from the lake where the new trout are coming from. All right, so 1 minus 0.1 would be 0.9, times it by the p-value of the original lake plus m times the p-value of the lake that the new trout are coming from. That gives us 0.56. Right, so if you look more closely at this formula, you'll notice that we're essentially trying to average out what the p-values are going to be, but it's a weighted average such that the larger the relative number of individuals coming in through migration, the more this is going to affect our final p-value, right? It also depends on how different they are from the original population as well. So the fact that the other population had a 0.2 p instead of 0.6, that's a pretty big difference, right? Which is why even though only 10% of the new trout only make up 10% of the final population, it actually drags down the final p-value quite a bit because it's a bigger difference, right? So if you look closely at this, essentially what we're saying is that, okay, for this new p-value, right, 90% of it's going to be based on our original p-value in this lake, right, because that's 90% of the final trout came from the original lake, and then 10% of our new p-value is going to come from the p-value of the source lake, the lake that's providing the trout that are migrating in. All right, so that's all that is. So 90% is 0.6, 10% is 0.2. That gives us 0.56 overall in the final lake population. All right, so hopefully that makes sense. If you have any questions about that, please feel free to send me an email or call me or drop by during office hours or during regular working hours. All right, let's look at one more example, which is going to be looking at natural selection. So we know that, as we talked about a lot today in class, that natural selection ends up decreasing the frequency of alleles that are bad and increasing the frequency of alleles that are good in terms of evolutionary fitness, good in terms of allowing you to produce larger and higher quality and quantity of offspring, so you can pass on your genes to more individuals in the next gene pool or population. Now, natural selection can be kind of complex because what counts as being beneficial is kind of depends on what other alleles you have and on what the environment is like. So let's start with a very, very simple example of a genetic disorder that is bad regardless of what the environment is like, mostly, right? So Tay-Sachs disease is a really bad genetic disorder because, in terms of evolutionary fitness, because it is a recessive lethal allele. All right, so when the phenotype is basically you die before you reach adulthood, that's as bad as things get in terms of evolutionary fitness. So let's assume that a population has a Q, so Q meaning the frequency of the recessive allele of 0.1. And so 10% of the gene pool is the recessive allele, the one that's lethal, that causes lethal Tay-Sachs disease. And let's say that mating is completely random with respect to this gene. All right. So what is the allele frequency in the next generation of adults? So here are your possible answers. Take some time to do your calculations, and we'll talk about this in a second. So please pause now. All right, welcome back. So this is a difficult question. Those of you who are very good at math and problem solving may have found the right answer, which is B. But if you got the wrong answer, then let's take a look at kind of how we found this number. All right. So in the question, we tell you that Q is equal to 0.1. So since P plus Q together gives you 1, then 1 minus 0.1 gives you 0.9 as P. All right. So since the question tells you that mating is random with respect to this gene, right, we're basically going to be able to use our Hardy-Weinberg equilibrium calculations for now in order to predict what the next generation should look like, because at least in terms of mating, we should be able to randomly draw alleles from our gene pool to make the next generation. And we will deal with the natural selection afterwards. You'll see what happens then. Right, so if we want to find out the frequency of homozygous dominant individuals, we basically just take the probability of getting a big A, which is 0.9, and times it by the probability of getting a second big A, which is 0.9 again. So 0.9 times 0.9 is 0.81. That gives us our genotypic frequency of homozygous dominant individuals. For heterozygous individuals, we go 0.9 times 0.1, which is 0.09, times 2, like 2pq, which gives us 0.18. And finally, for homozygous recessive individuals, we go q squared, which gives us 0.01. So we're using the Hardy-Weinberg equations to calculate what we would expect in terms of genotypic frequencies, because the question tells you that mating is random with respect to this gene. Okay, there's no sexual selection and whatnot. Now that we've predicted what should be generated when you're randomly mating this population that has a Q of 0.1, right, we then also have to think about, okay, well, the matings, when sperm are meeting eggs, these are the combinations we're putting together. But then after fertilization happens, and before these small a individuals reach adulthood, the small a individuals will die because they are homozygous for a recessive lethal allele. So we need to adjust our frequencies a bit, because as much as Hardy-Weinberg and random mating predicts we'll get this many big A, this many heterozygotes, and this many small a, we know that these now die, and now we have a problem that this becomes 0 as they die, and these no longer add up to 1. So we need to just adjust the frequencies of the ones that stayed alive so we can know what proportion is big A, and what proportion is big A, small a. So if we want to figure out the proportion that's big A, all we got to do is take our original frequency, and in order to make it so that these two together add up to 1, we just take it and divide by the total of these two, right? So since the 0.01 proportion of the population that's small a dies, we're left with a population that's kind of made up of 0.99. Right? We'll have 99% of the individuals left. So if we take our 0.81 divided by 0.99, we'll get this number. And for our heterozygotes, we take our original predicted proportion of heterozygotes, and again divide by 0.99. It's almost like our new total number of proportion of individuals to get this number. So the whole reason why we're doing this is because none of these small individuals survive. We just have to adjust these two numbers so that when you add these two together, you'll find that they add up to 1. Okay? So we made some adjustments, right? We correct this predicted value to know that even though random mating gives us this genotypic frequency, these ones will die before adulthood. So as they approach adulthood and all these die, what we're left with is 81.82% of the population is big A, and 18.18% is big A, small a, and that will add up to 100% now that we've made this adjustment because these ones died. Okay, so we can also get, so from this, our allele frequencies after this has happened. So we use this information here that mating is random to use the Hardy-Weinberg equilibrium, calculations and formulae to find out what should be produced during fertilization at least. Then we adjusted the proportions of what's found in the population, the genotypic frequencies, based on the fact that these ones then died. So we now want to find out, with this adjustment, with these ones dying, what is our new P and what our new Q, right? So P, the quickest way, shortcut way to get our P is basically to take our proportion of homozygous individuals and add half of the heterozygotes to get this value. So this is our P value after natural selection, after these small individuals died due to Tay-Sachs disease. The Q value, this you can do the same thing if we like. So we take the frequency of small individuals, which is now 0 because they all died, and we add half of the heterozygous individuals, that proportion, because these ones are still carrying a small a allele, and that gives us this as our Q value after the natural selection occurs. So one generation later. All right, so that is your final answer for this question up here. So what you essentially did was you predicted a genotypic frequency based on random mating. You killed off the small individuals. You adjusted the frequencies based on what's left over. So taking this frequency and dividing by the new total final frequency to make it out of 1. And from there we calculate the new P value and the new Q value based on the real genotypic frequencies. All right, so notice what happened. With natural selection, they have just one generation, right? And the small proportion of small a individuals, right? This 0.01, this 1% of the population dies. And because we've now removed a bunch of small a alleles from the gene pool, P and Q has changed. We have evolution, we have a shift in the allele frequencies in the gene pool in the population, such that we started off with Q being 0.1, and now that's dropped down to 0.0909. Okay, so we've lost 0.0001. Whereas in a proportional way, P has gone up. So P originally started off being just 0.9, and now it becomes 0.9091. Okay, so it's a small change, but think about this happening generation after generation for thousands or millions of generations. Over time, Q is going to go down, right? The allele frequency of this very, very bad for fitness allele will go down over time in this gene pool due to natural selection. Okay. Here's another example that's kind of interesting, a little more complex. So sickle cell allele, right? The small, it's now you can consider it being small a when it comes to sickle cell disease, which is a serious disorder, in that if you have one big A and one small a, you don't show very much of a phenotypic kind of symptom. All right. So when it's small a, you would have sickle cell disease. So you'd have very low fitness because it is relatively lethal. It's kind of hard to survive and reproduce when you have sickle cell disease. When you're big A, so you're homozygous for the wild type dominant allele, then you have completely normal blood. But the downside, if you're living in an area that has malaria, is that normal blood is quite vulnerable to malaria, so your fitness is not bad. And strangely, don't fully understand why, but when you have a heterozygous individual, where you'll see some of the cells being sickle-shaped, we call this sickle cell trait. Notice it's different from disease. Disease, when you have 2 copies of the recessive allele, and therefore very low fitness because you're showing the full sickle cell disease. When you're heterozygous, we call that having sickle cell trait, where the symptoms are very mild, which is why we kind of use big A here to symbolize that if you have just one good copy of the wild type allele, your symptoms are mild enough that we don't consider you as having the disease. But that small a, when it's heterozygous, does give you some very good resistance to malaria. Malaria just doesn't happen to be able to establish itself and harm you as much when you have the sickle cell trait. So in an area that has lots of malaria, at the high risk of getting malaria, a heterozygous individual has the highest fitness. For example, in a place in Africa, in a place such as Africa, where there's lots of malaria. So this is an example of the heterozygote advantage, right? It's a special situation that does come up in many different situations where the heterozygote does better than either of the homozygous individuals, and that makes it so that compared to what you'd predict with Hardy-Weinberg equilibrium, you end up seeing a higher frequency of heterozygotes. Okay, so this is what we actually see in African populations that have a high risk of malaria, is that rather than what we saw with Tay-Sachs disease, where you just get less and less of this deleterious recessive allele over time, we actually see lots of heterozygotes higher than is predicted by Hardy-Weinberg equilibrium, because there's a selective advantage, a natural selection selected advantage for being heterozygous. All right, so again, if you have any questions, I am around this weekend, next week. Most of the time, you can reach me by phone or by email. So just give me an email, let me know when you're free, and we can talk about whatever questions you have. Otherwise, I will have extra office hours from 11 to 2 in B9242 in the Monday and Tuesday before your final exam. All right, so thank you all very much. This has been an amazing semester for me. I feel like I've gotten to know you guys more than I normally get a chance to for BIS 202, since it doesn't have a lab. And so I really appreciate your open-mindedness with all the new things I've been trying, and for being supportive of this course and being so hardworking. So thank you very much, and hopefully I'll get to see you in other courses, or at least on campus. See you soon.